Hello guys, welcome to my YouTube channel, Usano-Goldie RL Marquez. This is Differential Equations, higher order linear differential equations with constant coefficients. In this video, I will be discussing differential operators and how they are applied to higher order linear differential equations. What is a differential operator? A differential operator is an operator that denotes differentiation. That is, when applied to a function, a derivative is obtained. Let D be a differential operator. Then, D with subscript x means first derivative with respect to x. D with superscript 2 and subscript x means second derivative with respect to x. D with superscript 3 and subscript x means third derivative with respect to x. And in general, D with superscript k and subscript x means kth derivative with respect to x, where k is equal to 1, 2, 3, all the way to n. In the notation D with superscript k and subscript x, superscript k means order of the derivative. Subscript x means the independent variable. D with superscript k and subscript x is normally written as D with superscript k disregarding the subscript. If no subscript is written, it is understood that it is with respect to x, unless otherwise stated. D with superscript k can be read as d to the k. So, D with superscript 2 is read as d to the second or d squared. D with superscript 3 is read as d to the third or d cubed. D with superscript 4 is read as d to the fourth. And so on. But you have to keep in mind that k means order and not exponent. The differential operator is appropriately called a derivative operator because it gives a derivative instead of a differential. When applied to a function y equals f of x, we get d with subscript x followed by y, or simply d followed by y means derivative of y with respect to x. And d with superscript k and subscript x followed by y, or simply d with superscript k followed by y means kth derivative of y with respect to x. D followed by y is read as d applied to y, while d with superscript k followed by y is read as d to the k applied to y. Let us have the following examples. Example number 1. Evaluate the given derivative. D applied to inverse tangent of x plus ln of x squared plus 1 plus 3 multiplied to x squared plus 1 quantity to the negative 1. Letter B. D cubed applied to e to the fourth x minus 5 cosine 5x plus 8x to the 7. D to the fifth applied to sine x minus cosine x plus 3 e to the x plus x to the fifth. And d to the 100 applied to e to the x plus sine x minus x to the 100. So let us have the first one. So getting the derivative of every term, we have for the first term, derivative of inverse tangent x, that is 1 over 1 plus x squared. derivative of ln x squared plus 1 is 2x over 1 plus x squared. Derivative of 3x squared plus 1 quantity to the negative 1 is negative 3x squared plus 1 quantity to the negative 2 times 2x. Combining the first two terms, we have 2x plus 1 all over 1 plus x squared. Then minus 6x all over 1 plus x squared quantity squared. Combining these two fractions, we get 2x cubed plus x squared minus 4x plus 1 all over 1 plus x squared quantity squared. So this is the first derivative of this sum of these three functions. Letter B. D cubed applied to e to the 4x minus cosine 5x plus 2x to the 7. So we have to take up to third derivative. Taking the first derivative, we get 4 e to the 4x minus derivative of cosine of 5x is negative. So we have positive. Derivative of 5x is 5. So we have 5 sine 5x plus 14x to the 6. For the second derivative, we have 16 e to the 4x plus 25 cosine 5x plus 84x to the 5th. Then for the third derivative, we have 64 e to the 4x minus 125 sine 5x plus 420x to the 4th. So this is the third derivative of e to the 4x minus cosine 5x plus 2x to the 7. Letter C. D to the 5th applied to sine x minus cosine x plus 3 e to the x plus x to the 5th. So we have to get up to 5th derivative. First derivative, we have cosine x plus sine x plus 3 e to the x plus 5 x to the 4th. Second derivative, we have negative sine x plus cosine x plus 3 e to the x plus 20x cubed. Third derivative, negative cosine x plus negative sine x plus 3 e to the x plus 60x squared. Fourth derivative, sine x minus cosine x plus 3 e to the x plus 120x. And for the fifth derivative, which is the last one, we have cosine x plus sine x plus 3 e to the x plus 120. So this is the fifth derivative of sine x minus cosine x plus 3 e to the x plus x to the 5th. Letter D. D to the 100 applied to e to the x plus sine x minus x to the 100. So let's take first sine to the x. So let's get a pattern for this. If we have y equals sine x, its first derivative is cosine x. Second derivative is negative sine x. Third derivative is negative cosine x. Fourth derivative is also sine x. And then if you're going to get the derivative of this, which is the fifth derivative, you will get cosine. Sixth derivative, negative sine x. Seventh derivative, negative cosine x. And then eighth derivative will go back to sine x. And then 16, and so on. So it means the 100th derivative will fall here. So it is also sine x. Hence, the 100th derivative of sine x is sine x also. What about x to the 100? So again, let's have a pattern. Let's say I have x to the first, getting its first derivative, that is 1 or 1 factorial. If I have y equals x squared, its first derivative is 2x, its second derivative is 2 times 1, which is 2 factorial. Y equals x cubed. Let's get the third derivative. So the first derivative is 3x squared. second derivative is 3 times 2x, and the third derivative is 3 times 2 times 1 equals 3 factorial. So, if I'm going to get the derivative of x to the n, so I will get from the pattern n factorial. Hence, the derivative of x to the 100 is 100 factorial. And for the derivative of e to the x, it is always e to the x. So 100th derivative of e to the x is e to the x. Hence, the 100th derivative of e to the x plus sine x minus x to the 100 is e to the x plus sine x minus 100 factorial. General form of a differential operator of order n. A differential operator of order n takes the form a sub 0 d to the n plus a sub 1 d to the n minus 1 plus a sub 2 d to the n minus 2 all the way to a sub n, where a sub I is equal to g sub I of x, meaning they are all functions of x, the coefficients of these individual operators up to this last term a sub n, for all I equals 1, 2, 3, all the way to n. Let's call this, for simplicity, phi of d. When a differential operator of order n is applied to a function y equals f of x, we have a sub 0 d to the n plus a sub 1 d to the n minus 1 plus a sub 2 d to the n minus 2 all the way to a sub n applied to y. This is equal to a sub 0 d to the n applied to y plus a sub 1 d to the n minus 1 applied to y plus a sub 2 d to the n minus 2 applied to y plus all the way to a sub n times y. So take note that d to the n applied to y is not identical or equal to y d to the n. There are operations in algebra that are also obeyed by differential operators. Let A and B be differential operators and C any constant. Then the following operations on differential operators hold. Sum of A and B, denoted by A plus B. The sum of A and B when applied to y gives us A applied to y plus B applied to y. Difference between A and B denoted by A minus B, similar to sum. So when A minus B is applied to y, it gives us A applied to y minus B applied to y. Product of A and B denoted by AB. When AB is applied to y, it is equal to A applied to B applied to y. So meaning, the first operator that we are going to apply to y is the one that is nearer to y. Then after that, A. Is scalar product of C and A denoted by CA. So again, C here is constant. CA applied to y, that is equal to C times A applied to y. And that is also equal to A applied to CY. There are properties of algebra that are inherited by differential operators. Let A, B, and C be differential operators, and M and N be positive integers. Then the following properties of differential operators hold. Associative property. A added to the sum of B and C is identical to the sum of A plus B added to C. For product, A multiplied to the product of B and C is identical to the product of A and B multiplied to C. Commutative properties. For addition, A plus B is identical to B plus A. But for the product, AB is not equal to BA in general. Distributive properties. A multiplied to the sum of B and C is identical to AB plus AC. Note that AB is not the same with BA because in general, AB is not equal to BA. So same thing for AC, it's not identical to CA. So this A multiplied to the sum of B and C is identical to just AB plus AC. Sum of A and B multiplied to C is equal to AC plus BC. Take note of the order of the product. AC plus BC. So again, AC is not equal to CA and BC is not equal to CB. Exponential properties. If I have an operator of order n multiplied to an operator of order n, that is equal to or identical to operator of order m plus n. So if I have an operator of order m and this A of order m has an order n, so that operator has an order mn. If all the coefficients of A and B are constants, then it is true that AB is equal to BA. Let us have example number 2. Expand, that is, perform the indicated operation on the differential operator D. So let us have the following. So for letter A, to expand an operator of order n, we apply it to a function. So applying it to y equals f of x, we have d multiplied to d plus x squared applied to y. So we first apply d plus x squared. So this is our A and this is our B. So applying b to y, so that is d applied to y plus x squared y. So d this time is to be applied to the sum. So it means second derivative of y, then derivative of this product. So d squared applied to y plus differentiating product, the first, derivative of the second, so d applied to y, plus the second y, then derivative of x squared. So, and that is 2xy. So, we get d squared applied to y plus x squared, d applied to y plus 2xy. Moving the y to the right of the operator, so we have d squared plus x squared d plus 2x applied to y. Hence, d multiplied to d plus x squared in expanded form is d squared plus x squared d plus 2x. Letter B, d plus x times d minus x. So let's apply it to a function y equals f of x. So d plus x, d minus x applied to y. So first we apply d minus x to y. So d applied to y minus xy. Then we apply d plus x to this difference. So d applied to y minus xy plus x times d applied to y minus xy. So we get second derivative of y, or that is d squared applied to y minus derivative of xy plus x derivative of y minus x squared y. So differentiating this product, we have negative x derivative of y plus y derivative of negative x is negative y. So we have xd applied to y minus x squared y. So these two are cancelled. So getting d squared applied to y minus x squared y. Let's move y to the right. So getting d squared minus 1 minus x squared applied to y. So hence d plus x, d minus x when expanded is given by d squared minus 1 minus x squared. Letter C, d minus x, d plus x. Applying it to y equals f of x. So we get d minus x, d plus x applied to y. So we apply first d plus x to y. So getting d applied to y plus xy. Applying the second operator to this result, we have d applied to d applied to y plus xy minus x times d applied to y plus xy. So we get second derivative of y plus derivative of xy minus x derivative of y minus x squared y. For derivative of this product, we have x derivative of y plus y derivative of x. So derivative of x is 1, so we get y. We copy x derivative of y and then x squared y. So this is cancelled with negative x derivative of y. So we get d squared applied to y plus y minus x squared y. So moving y to the right, d squared plus 1 minus x squared. So d squared plus 1 minus x squared applied to y. So hence, d minus x, d plus x in expanded form is d squared plus 1 minus x squared. A while ago, we got d plus x, d minus x as d squared minus 1 minus x squared. And for d minus x, d plus x, the expanded form is d squared plus 1 minus x squared. Notice that they are not equal. So it means that AB is really not generally equal to BA. xd plus 1 multiplied to x squared d. So let's expand this operator. So applying it to y, we have xd plus 1 multiplied to x squared d applied to y. So applying x squared d to y, so we get x squared derivative of y. So this second operator, so xd plus 1 applied here, so we get xd applied to x squared derivative of y plus x squared derivative of y. So this is product. So x times, so the derivative of this is x squared, second derivative of y plus derivative of y times 2x. So plus x squared derivative of y. Distributing x inside the parentheses, we have x cubed second derivative of y plus 2x squared derivative of y plus x squared derivative of y. So these are similar terms. We can combine them into 3x squared derivative of y. Then plus x cubed the second derivative of y. Moving y to the right, we have x cubed second derivative of y plus 3x squared first derivative of y. So we have xd plus 1 x squared d is therefore equal to an expanded form x cubed d squared plus 3x squared d. Example 3. Expand, that is perform the indicated operation on the differential operator d. So we have 4 products. So for the first one, so notice that actually in all these products, all the coefficients are constants. So to multiply them, so all we have to do is to treat d as an ordinary variable. And we can apply ordinary operations in algebra. So d times d plus 4 is identical to d squared plus 4d. d minus 2 times 3d plus 4, we have 3d squared plus 4d plus negative 6d plus negative 8. Or we have 3d squared minus 2d minus 8. D squared plus 4, d minus 1. So we have d cubed minus d squared plus 4d minus 4. And then d minus 3, d plus 3, 2d minus 1. So the product is, for the first two factors, we have d squared minus 9. And then multiply to 2d minus 1. So we have 2d cubed minus d squared minus 18d plus 9. General form of a linear differential equation of order n. A linear differential equation of order n takes the form a sub 0 nth derivative of y with respect to x plus a sub 1 derivative of y with respect to x of order n minus 1 all the way to a sub n minus 1 y prime plus a sub n y equals r of x. To be able to apply operations and properties of differential operators to this LDE of order n, we're going to express this in d notation. So in d notation, we have a sub 0 d to the n plus a sub 1 d to the n minus 1 plus a sub 2 d to the n minus 2 all the way to a sub n applied to y equals r of x, where a sub I equals g sub I of x for I equals 1, 2, 3 up to n. So for simplicity, we will be calling this phi of d applied to y equals r of x. So example 4, the following are linear differential equations. This is in prime notation, 2xy double prime plus 5y prime minus x cubed y minus x equals x minus e to the 3x. In d notation, we have 2x d squared plus 5d minus x cubed applied to y equals x minus e to the 3x. Y triple prime plus 5y double prime minus 2y prime minus 10y equals 0. In d notation, we have d cubed plus 5d squared minus 2d minus 10 applied to y equals 0. Linear differential equations are generally classified into two groups. Linear differential equations according to the coefficients a sub i's, and linear differential equations according to the right-hand side r of x. So under linear differential equations according to the coefficients a sub i's, we have LDE with constant coefficients and LDE with variable coefficients. For linear differential equations according to the right-hand side r of x, we have homogeneous LDE or HLDE and non-homogeneous LDE or NHLDE. Take note that the term homogeneous here in higher order DE has nothing to do with the homogeneous term used in the first order, first degree ordinary differential equations. According to the coefficients a sub I, so we have LDE with constant coefficients. So when do we say that it is LDE with constant coefficients? When all the coefficients a sub i's are constants. The following are linear differential equations with constant coefficients. So the coefficient of the derivatives and the dependent must be all constants. So constant, 1 here, 4. So we don't care the right-hand side because this is r of x. Our reference, a sub i's. 1, 6, negative 1. So here in letter D, 1, negative 3, positive 2 as the coefficients of the derivatives and the dependent variable y. 1, negative 4. And for the second factor in the operator 1, then this is 1. Of course, when expanded, so all of the coefficients will be constants. 4, -3, -33, -70, -3. So this is also LDE with constant coefficients. Linear DE with variable coefficients. So when at least one of the coefficients A sub I is not constant. So the following are linear differential equations with variable coefficients. So we have, this is constant, this is 5x to the fourth, -1. So there is one coefficient that contains variable, which is in terms of independent. So this is also LD with variable coefficients because the coefficient of y triple prime and the dependent variable y are all functions of x. So letter C, so we have 2x for the coefficient of y double prime. So we have -x cubed. So there are two variable coefficients. So -3e to the x, e to the 2x. So still LDE with variable coefficients. So we have 4x. So this is LDE with a variable coefficient. So also for the last one. Linear differential equations according to the right-hand side. Homogeneous LDE. So when do we say that it is a homogeneous LDE? So if the right-hand side of linear differential equation of order n is equal to 0. So examples, we have, this is the right-hand side, r of x, 0. So 0 for the second one. Also 0 for the third. 0 for the fourth. R of x for the, for the fifth. So this is actually E. And then for F, we have also 0 on the right side. So all of these are homogeneous LDE. Non-homogeneous LDE, so NHLDE. So when R of x is not equal to 0, so that is non-homogeneous LDE. The right-hand side is not 0. So the right-hand side is 4. Here, tangent of x. So x minus e to the 3x for letter C. And then we have x e to the x cosine x for letter D. For letter E, we have square root of x. Letter F, ln x. So they are non-homogeneous LDE. Linear differential equations, non-homogeneous. What is the form for the general solution of linear differential equation of order n? So the general solution of LD of order n takes the form y equals y sub c plus y sub p, where y sub c is the complementary function or solution, which is the solution of the associated homogeneous LDE, phi of d applied to y equals 0. So, and it takes the form c sub 1 y sub 1 plus c sub 2 y sub 2 plus c sub 3 y sub 3 all the way to c sub n y sub n, where c sub 1, c sub 2, c sub 3 up to c sub n are all arbitrary constants. The number of arbitrary constants is equal to the order of the differential equation or the HL, the given linear DE. Y sub p here is a particular solution, so it means it does not contain any arbitrary constants. So which must satisfy, so this must satisfy the non-homogeneous LDE phi of d applied to y equals r of x. So that is, if I replace y by y of p, then phi of d applied to y sub p is equal to r of x. So this y sub p takes the form y sub p sub 1 plus y sub p sub 2 plus y sub p sub 3 all the way to y sub p sub k. The number of terms here does not depend on the order of the differential equation. If the LDE is homogeneous, y sub p is 0. So the general solution of homogeneous LDEs y equals y sub c. And if the linear differential equation is non-homogeneous, yp is not equal to 0, and the solution, general solution is y sub c plus y sub p. Solving homogeneous LDE by reduction of order. So this makes use of reducing the given linear differential equation of order n to order n minus 1 until order 1 is obtained. Solve the LDE, d squared plus 4d minus 3 applied to y equals 0. Let's factor this operator. So d squared plus 4d minus 3 when factored is equal to d plus 4 times d minus 3. So it is also identical to d minus 3, d plus 4 because commutative property holds since all the coefficients are constants. So this differential equation with differential operator in factored form is d plus 4d minus 3 applied to y equal to 0. To solve this by using reduction of order, we are going to replace this d minus 3 applied to y by a simple variable. Let's say w. Hence, this becomes d plus 4 applied to w equals 0. Equivalently, derivative of w with respect to x plus 4w equals 0. So which is LDE. Let's label it equation 1. Integrating factor of this is e to the integral of 4 dx, which is equal to e to the 4x. This can also be solved by separation of variables. General solution of 1 is given by w e to the 4x equals integral of 0, that is the right hand side here in 1, times e to the 4x, the integrating factor, dx plus k1. Since this is 0, the integral is simply a constant, plus k sub 1. So let k sub 0 plus k sub 1 be simply k sub 2. So that is equal to w e to the 4x. Isolating w, we multiply by e to the negative 4x. So we have on the right side k sub 2 e to the negative 4x. And the left, w. So, but w here in w equals k sub 2 e to the negative 4x is equal to d minus 3 applied to y. So this equation becomes d minus 3 applied to y equals k sub 2 e to the negative 4x. So equivalently, y prime minus 3y equals k sub 2 e to the negative 4x, which is a linear DE. Integrating factor is the integral of e to the negative 3 dx. So the coefficient of y, which is negative 3, is the p here. Then we get e to the negative 3x. General solution of the given DE or this DE. So y e to the negative 3x equals integral of k sub 2 e to the negative 4x times e to the negative 3x dx plus k sub 3. This is the q and this is the I of x. So this is e to the negative 7x. Move the k sub 2 out of the integral sign because this is constant. So we can integrate this using e to the u. So e to the u multiplied by negative 7 balanced by negative 1 over 7. So we have negative 1 over 7 k sub 2 e to the negative 7x plus k sub 3. So that is equal to y e to the negative 3x. So isolating y, we multiply by e to the 3x. So we get y equals negative 1 over 7 k sub 2 e to the negative 4x plus k sub 3 e to the 3x. Let's put negative 1 over 7 k sub 2 as c1 and k3 c2. Hence, we have y equals c sub 1 e to the negative 4x plus c sub 2 e to the 3x. So, which is the general solution of the given DE. The reason behind of putting this into C1, C2 to comply or to put it in the form of YC, y equals y sub c plus y sub p. So happens that y sub p here is 0 and y sub c has the form c sub 1, y sub 1, c sub 2, y sub 2, and so on. For this case, sa second order DE, so we have two arbitrary constants. So we have the order is 2. So equal to the number of arbitrary constants. So c sub 1, y sub 1 plus c sub 2, y sub 2. Solve the linear DE, d squared minus 8d plus 16 applied to y equal to 0. Again, let's factor this differential operator. So this is perfect square trinomial, d squared minus 4 quantity squared. Hence, we have d minus 4 quantity squared applied to y equal to 0. So let one of these, d squared minus 4 applied to y, be w. So there is a remaining d minus 4. Then apply it to w equals 0. Equivalently, this is derivative of w with respect to x minus 4, w equals 0, which is LDE or a separable DE. So integrating factor is e to the integral of negative 4 dx, so e to the negative 4x. General solution of 1 is given by w e to the negative 4x equals integral of 0 times e to the negative 4x dx plus k sub 1. So this is 0 e to the negative 4x. So we have k sub 0 plus k1. Integral of 0 is constant. Let this be k sub 2. Isolating w, we have w equals k sub 2 e to the 4x. But w is d minus 4 applied to y equals k sub 2 e to the 4x. Integrating factor of this is e to the integral of negative 4 dx, so e to the negative 4x. General solution, y e to the negative 4x equals integral of k sub 2 e to the 4x times e to the negative 4x dx plus k sub 3 equals k sub 2 integral of dx. This is cancelled with e to the negative 4x plus k sub 3. So we have k sub 2x plus k sub 3. Multiply each side by e to the negative 4x. So we have k sub 3 plus k sub 2x multiplied to e to the 4x. So that is equal to y. So this is the general solution. But let us express this so that arbitrary constants are c1, c sub 2. So k3 is c1 and k2 is c sub 2. So we get c sub 1 plus c sub 2x multiplied to e to the 4x. Or you can have it c1 e to the 4x plus c sub 2x e to the 4x. You can expand the right side. Solve the LDE d squared plus 4 applied to y equal to 0. Although this has no real factors, factors that have real coefficients, but we can still factor that with imaginary coefficients. D squared plus 4 is d plus 2i, d minus 2i. D plus 2i, d minus 2i applied to y equal to 0. So that is the differential equation given. Let d minus 2i applied to y be equal to w. So we have d plus 2i applied to w equal to 0. So this is dw. dw over dx plus 2i, w equal to 0. Our p here is 2i, our q is 0. So label it equation 1. Integrating factor is e to the 2ix. So general solution of 1 is w e to the 2ix equals integral of 0 times e to the 2ix dx plus k1. So this is 0. The integral is k sub 0 plus k1 here. Let this be k2. Isolating w, we have k2 e to the negative 2ix. D minus 2i applied to y, that is w equals k sub 2 e to the negative 2ix. So integrating factor is e to the negative 2ix. General solution, y e to the negative 2ix equals integral of k sub 2 e to the negative 2ix times e to the negative 2ix dx plus k sub 3. So this is e to the negative 4ix. So times k sub 2, integral of this, plus k sub 3. So we put negative 4i balanced by negative k sub 2 over 4 sub 4i. So balanced by negative 4, negative 1 over 4i, So times k sub 2. So e to the u du. E to the u du, we get integral of that e to the negative 4ix. So e to the u times k sub 2 over 4i plus k sub 3. Isolate y, multiply by e to the 2ix. That is equal to y is equal to negative k sub 2 over 4i e to the negative 2x I or 2i negative 2ix plus k sub 3 e to the 2ix. So y equals k sub 4. Let's simplify this arbitrary constant to k sub 4 e to the negative 2ix plus k sub 3 e to the 2ix. But in complex analysis, e to the negative 2ix equals cosine 2x minus I sine x. Our goal is to put this so that no imaginary I. So we can do that by using these identities. E to the 2ix equals cosine 2x plus I sine 2x. So we have y equals k sub 4 times e to the negative 2ix is cosine 2x minus I sine 2x. Then e to the 2ix is equal to cosine 2x plus I sine 2x. So times k sub 3. Let's expand. K sub 4 cosine 2x minus I k sub 4 sine 2x. K sub 3 cosine 2x plus I k sub 3 sine 2x. Collecting these two terms having both cosine. So k sub 4 plus k sub 3 multiplied to cosine 2x. Combining those with sine functions. So we have negative k sub 4 plus I k sub 3. Negative I k sub 4 plus I k sub 3 multiplied to sine 2x. So let's simplify this arbitrary into C1. And this arbitrary I k sub 4 negative plus I k sub 3 into C2. So hence, this general solution becomes y equals C sub 1 cosine 2x plus C sub 2 sine 2x. So that's the general solution. So thank you for watching. Please don't forget to subscribe to my YouTube channel so that you can have an update of other videos and more videos that are coming. Usano-Goldie RL Marquez. So that's my channel. So goodbye.